All right, so let's step back and go back to the idea of the universe expanding. So when we consider the expansion rate of the universe, how fast it's expanding, it's actually naive to think that the expansion rate today is the same as it has always been. Okay, so for example, we know of other forces that can act on a universal scale that should be influencing this, particularly gravity. Gravity is always attractive, so it's always pulling stuff in, and then what that should do is slow down the expansion rate of the universe. Okay, so we kind of get this idea that the expansion rate should be changing in time. Okay, well, we can actually do observations to see how this has happened. So in this graph, along the bottom, we have the redshift z. Okay, so this is going to be related to how fast the universe is expanding. So remember, this is cosmological redshift, which is redshift caused by the expansion of space. Okay, so this is going to be related to how fast the expansion rate is happening. And then up and down, we're looking at the apparent magnitude of supernova. In other words, brightnesses. And if you remember back, we can use the brightness and luminosity to figure out distance. And because we know distance, we can figure out how far back in time. Because the farther away something is, the farther back in time we're actually looking. Okay, so up and down, we have the apparent magnitude of supernovae giving us distance and also time. Okay, so as we look at this graph, what we've actually found is that the universe is speeding up in its expansion. The expansion rate today is faster than it was in the past. When this was first discovered, this was a huge breakthrough. Like, this was mind-boggling. Nobody understood what could possibly be going on. Okay, what we believe is going on is that this is the effects of dark energy. Dark energy is acting as kind of an anti-gravity, speeding up the expansion rate of the universe. Okay, so in this graph, along the bottom, we're looking at the amount of matter in the universe. This includes normal matter as well as dark matter. And then up and down on this graph, we're looking at dark energy, how much dark energy is in the universe. Now, each of these colored regions corresponds to different possibilities based on different observations. Okay, so the blue region through here, this is what is possible based on supernova data. Okay, so what we just talked about with looking at the supernova and redshift. Okay, the green region is what is possible based off of the cosmic microwave background. And then this kind of brown-orange region is what is possible based off of the size and scale of galaxy clusters. Well, as we look at these, the only place that all of this data agrees that it actually matches is right here where this red dot is. And that red dot corresponds to a universe that is made of 68% dark energy, 27% dark matter, and only 5% normal matter. 5% of the stuff that we actually see and understand. Okay, what this means is that 95% of our universe is still stuff that we don't understand. Now, this is actually great news because it means that astronomers still have jobs trying to figure out what's going on. With this understanding, we can now predict how the universe is going to end. So we stated previously, because of the amount of dark energy in the universe is dark energy dominated. Well, what we now know is that dark energy is leading to the acceleration of the expansion of the universe. And so what's going to happen eventually is galaxy clusters are going to continue to drift farther and farther away from each other. And eventually they'll be so far apart and moving away from each other so quickly that any visible light they have will be redshifted to the point of invisibility, out into the infrared or beyond. Then within galaxies, eventually they will use up all of their interstellar medium, so new stars are going to form. And then stars are going to die. First the high mass, and then the medium mass, and then even eventually the low mass stars are going to die out. So the eventual state of the universe is going to be perfectly cold, perfectly black, and completely depressing. So I actually don't like to think about it too much. But based on our current understanding, that's what we believe is going to happen eventually. Well, going back to an idea that's a little bit better, with our understanding of the expansion rate of the universe, we can actually go backwards in time to figure out how old the universe is. So looking at the expansion rate and the energy density and everything of the universe, we can trace back to say that the universe began about 13.8 billion years ago. This is a number that I recommend that you know. 13.8 billion years ago.